Welcome to my channel Physics Infinity. I bring to you in this lecture specialized techniques to solve effective resistance network problem, to find the effective resistance of a network. Now remember, whenever we have a complicated looking resistor network, we should be asked to find the effective resistance between 2 points. These 2 points are called the cell points, and the line joining them is the hypothetical line, imaginary line joining them is called the cell axis. The perpendicular bisector of this cell axis is called perpendicular bisector to the cell axis. Now let me tell you one thing. You face a lot of questions based on the effective resistance of a network in examinations like the JEE, the NEET. There are very specialized techniques to find the effective resistance of the network that normally I teach in class. The reduction method, the superposition method, Thevenin concept, the Thevenin theorem, symmetry across the cell axis, symmetry across the perpendicular bisector of the cell axis, star delta, delta to star, star to delta, etc. And of course, then you have the KCL and the KVL, the Kirchhoff's current rule and the Kirchhoff's voltage rule. Here, I am going to emphasize on 2 techniques, that is symmetry across the cell axis and symmetry about the perpendicular bisector of the cell axis. To illustrate this, I take on a beautiful network of resistors. Here you are. There is a delta within a delta, ABC and DEF, and all the resistors shown to you in red are 1 ohm. All resistances are 1 ohm. We are asked to find the resistance across AD. So AD are the cell points. And another question across BC. Then BC are the cell points. I take the questions one by one. Let me first find RAD, resistance across the points AD. So AD are the cell points. As if there is an imaginary cell connected across the points A and D. A and D. So, if current I enters at A, well, it should leave at D. These are the cell points. There is an hypothetical imaginary cell across the points AD. Now, what I've just told you, AD is the cell axis. So I extend it. So A, D, G, H, all this is cell axis. Now observe the cell axis coolly. You will observe something very interesting, that there is a complete symmetry about the cell axis. Look, if this is the cell axis, I have 1 ohm here, 1 ohm here, 1 ohm here, 1 ohm here. And even if this is 1 ohm and this is 1 ohm, I can break it into half here and half here. So half here, half here. Same thing here between BC, half ohm here and half ohm here. As if the network folds about the cell axis. In such a, now what is the technique? If you observe a symmetry about the cell axis, then find the mirror images. Treat the cell axis like a mirror and the corresponding mirror images. You'll observe 2, B and C, E and F. These are the mirror images, and the technique is that these mirror images are the EPP, equipotential points. If these are equipotential points, then the resistance between them can be ignored. The resistance between them can be ignored. I ignore it. So I redraw the circuit by ignoring the resistance EF between EF and between BC, because EF and BC are EPPs, equipotential points, gone. If they are gone, look at that. Now, in 1 second you can solve the problem now. So between across AD you have 1 ohm, then you have 1, 1, 1, 3 ohm, 1, 1, 1, 3 ohm. So 1 ohm parallel to 3 ohm parallel to 3 ohm. 3, 3 parallel becomes 1.5. So 1 parallel to 1.5. 1.5, 1 into 1.5 upon 1 plus 1.5, 1.5, that becomes 15 upon 25, that becomes 3 by 5. Done. The problem is solved. The effective resistance across AD is 3 upon 5 ohms. Now, let's go to the question number 2. In the question number 2, we have been asked to find BC, resistance across BC. Well, if I take BC, so BC are the cell points, but if I take BC as the cell axis, I see nothing below the cell axis. So forget about the symmetry across the cell axis. Let me now try out the next technique, that is symmetry. Is there symmetry about the perpendicular bisector of the cell axis? I draw the perpendicular bisector. So A, D, G, H. This is the perpendicular bisector of the cell axis BC. Observe it carefully. Observe this perpendicular bisector carefully. You will observe that there is symmetry. There is symmetry about the cell axis, about the perpendicular bisector. What is the perpendicular bisector? ADHG. We have just done that. So about the perpendicular bisector, there is symmetry. Check it out. 1 here, 1 here, 1 here, 1 here, half here, half here, half, half. Yes, there is a beautiful symmetry about the perpendicular bisector. Now, what's the technique? The technique is that if there is symmetry about the perpendicular bisector, then all points on the perpendicular bisector are EPPs, are equipotential points. If they are equipotential points, then what are the equipotential points? ADGH. ADGH. They are equipotential points. So they can be joined as one point. And any resistance between these points can be ignored. Well, I find only the resistance AD lying on the perpendicular bisector, which has to be ignored. I redraw the circuit. Here. So ADGH, they are equipotential points. All 4 points are 1 point. You have B here and you have C here. Now resistance BC is technically RBH plus RHC. But RBH is same as RBA, because H and A are same points. So this is RBA plus RCA. RBA and RCA, as the symmetry shows, are equal. So I just calculate RBA, then I'll multiply by 2. I get the answer RBC. Let's do it. ADGH, 1 point. B is here. Now just go on observing. Between AB there is 1 ohm. I draw it. Between BE 1 ohm. Okay. Between EA 1 ohm. I draw it. Now between E, look at that. Between E and D is here. D is same as A. So between E and D, there is half ohm. There is between E, look at that, this one, because G and D are same points. So this is half ohm. And there is another half ohm. Look at this one. B and H is here. There is half ohm. Now I don't write for this one because it is same as this one by symmetry. I just calculate RBH, which is same as RBA. Now look at this. I put the 2 points here. So RAB 1, then this one 1.5 parallel, 1 into half upon 1 plus half becomes 1 by 3. 1 by 3 series with 1 becomes 4 by 3, and this is half. So technically between these 2 points I have 1 ohm parallel to 4 by 3 parallel to half. Solve it out. Elementary thing, elementary maths. So it is 1 by 3, 1.5 parallel is 1 by 3. So 1 by 3 parallel to 4 by 3. Product upon sum. 1 by 3 into 4 by 3 upon 1 by 3 plus 4 by 3. I get 4 by 15. So 4 by 15 is RBH or RBA, same thing. And same thing RHC, 4 by 15. So what is the effective resistance across BC? 8 by 15. Twice of 4 by 15, that is 8 by 15. Done. The problem is solved. I hope you have liked the video. I'll bring another video.
If you love the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.